it's going to be like a combination of approaches of DeepMind and OpenAI. And in the middle, I feel like we all felt like OpenAI and these transformer-based frontier labs, they're going to win this battle. But I think it was 2024, 2025 when you and I started discussing, and we're like, you know what, this is not going to work. They're often thought of as a machine, but they operate more like an organism, right? It's reacting to its external environments, right? So there's always that back and forth. It's reacting to what's happening outside, and then that is changing the context of the context around the enterprise, and then everything has to evolve based on that, right?
So basically, we give it to a slightly better model, and then we say, generate question answer pairs for this document, which we then train on the smaller model that we're trying to do this for. So here we were using a 0.5 billion, so a 500 million model. My name is Ammar Adeel, and I am leading machine learning at Y Industries. And I'm today with the CEO of Y.
By the way, can we just address how nice this looks? पीछे से
नहीं, मैं वही कह रहा था यार, मैंने तो ये
है ना?
नकली बैकग्राउंड लगाया हुआ है. आपका इज वेरी नाइस.
And it's like, I like this. I think we should do it during this time. It sort of like gives more like Gandalf and Lord of the Rings feels to the video. But khair, I think let's start. Ammar, thank you so much for us doing this. But I think this is good because we get to talk about our research. Typically, we don't even we have not been publishing our research, and I think now we're thinking of like redoing that and talking about what we have been working on. So just to start off, and I'll take some lead, and we can then sort of like keep it open. So I think essentially just to talk about, and because the audience is general public, uh, but also it's primarily our own internal team. So I would be referring to our internal team in these videos too. But I think our main focus for the last 2-3 years was towards open-endedness and everything that sort of like comes from there, right? So for anybody who does not understand open-endedness, it's sort of like an idea that took off in 2019. There was a paper written by Uber, and they were talking about how open-ended agents can sort of like learn and solve problem, which symbolic systems and just deep learning system with simple training can't really do, because it has like all of like it comes up with solutions, and it has like an objective, and it keeps exploring new and new options, and we always thought that's kind of like the future. And that's why we started our company in the first place. But then while there was a lot of exploratory work happening, ChatGPT came out, and obviously we were following transformer models for a while, but we were also looking into a lot of like other type of like models. And for a moment it felt like, yeah, we might have been wrong about what superintelligence is going to look like, and what these systems of the future and autonomous systems are going to look like. And there was a degree of nervousness that I had in 2024, 2023, because I was following GPT-3 and OpenAI for a while, right? And I thought always that it's going to be like a combination of approaches of DeepMind and OpenAI. And in the middle, I feel like we all felt like OpenAI and these transformer-based frontier labs, they're going to win this battle. But I think it was 2024, 2025 when you and I started discussing, and we're like, you know what, this is not going to work. And this is kind of this sort of like going in the wrong direction, because compute and data is not just going to solve all their problems. And we started working on our own pipelines, and we started sort of like not exploring again, but sort of like doubling down on what we believed in. And I'm just going to take some time talking about that. So essentially, our belief is that any super intelligent system, and we don't want to talk about AGI, we'll just say super intelligent systems, because I think and we think those are going to be domain specific. But super intelligent systems are going to become super intelligent because of two things. Number one, because of a deep understanding of context, right? And number two is going to be open exploration based on certain objectives which are not human sort of like devised, and sort of like agents having their own intent, their own motivations, exploring those options. So this is one of our first papers that we wrote, which is on self-evolving AI. And the idea initially was that, to because we have been working on self-evolving a lot now, and there are a lot of other things that we have done, but in this is sort of like one of our first papers, and we're excited to share our new research with you guys. But we're not ready for that today. But essentially, in self-evolving, and as Ammar took the liberty of writing auto-evolving agents when the title was being decided, we were basically looking into a system where we have given a bunch of AI agents tools to retrain themselves, to enrich themselves with the right context, to reduce their own size, to sort of like create their own GPRO policies, right? And what happens if you have defined an objective to them, and they have all of these tools, and the pipeline has all of these tools where it can sort of like choose, like a buffet, which direction they want to go into, right? So in this particular paper, we thought it'd be interesting if we gave a direction to a very small model, 500 million parameters, and we asked it to be to find to keep iterating itself to become comparable in performance to GPT-4o, right? And this is obviously again some time back, and right now it's sort of like we feel like we can even go lower than 500 million parameters, or we can make 500 million parameter model do much more complicated tasks. But in here, I think we were exploring RAG based application for complex data. And when we say complex, we mean data where you don't really have a simple answer, where you need to sort of like reason out an answer, where one document needs to be referred to another document, needs to refer to another document. But it was a biosciences company that we explored this with. And as you understand, being in biosciences space is it's very complex, and simple fine tuning would not be enough, right? So I think in this particular video, we will be talking about what we learned and what happens when you give a pipeline all of this access, right? And it is able to sort of like decide what it wants to do. And I think one thing I'm going to talk about, which was the coolest part about this pipeline, I would say. I mean, for me, it was the coolest part. I think I think I don't know which iteration it was, but the particular iteration where it sort of like quantized itself to 4 bits, I think, and then it realized itself that okay, I have quantized myself to 4 bits, but my performance and my accuracy is sort of like has gone down. So I'm going to go back to 8 bits, and I'm going to increase my accuracy, and that's the equilibrium that I have. Now, this is something that I can't do anything about until more data comes in for me to fine tune myself again, right? That level of understanding, right? To be able to sort of like decide that, you know what, now this is my sort of like equilibrium, and I can't move anywhere right now, and I've explored every other option. I feel like this is something which is very interesting. And needs to be explored further, and I think we have been working on that. And I think our main Ammar idea has been that um, don't overthink this. Everything else is fine. Just give them more tools, right? Just give them more and more tools, right? And just let them sort of like discover themselves what they want to do. So, Amma, jumping right into the paper, do you want to run us through the paper and exactly what are the tools that we enabled them to have, and what are the benchmarks that we were able to sort of like hit?
Thank you so much for the detailed background and context on this. Um, So maybe I'll just. So basically, with any system, when these models came out, the only sole knowledge base or the knowledge point of truth was the model itself. RAG came in later on, and then
Yeah.
so basically you could only just fine tune it, and that was basically it. And then prompt engineering came along, and then GRPO, or basically policy optimizations came along. So we basically needed to say, we say a model learns by itself. So whatever data comes in, if either you're tuning it like training it explicitly, or doing it implicitly due to the answers that it gets or the feedback that it gets. So but to basically narrow things down and just start with a few things, we said, okay, we'll just go along with um, three, four things basically. So that first one was auto fine tuning. So basically, supervised fine tuning, um, or training an adopter on top. So basically, that's also like fine tuning an adopter. Reinforcement learning. So how the model is answering instead of what it's answering, so the style of it basically. And then we have context engineering, so that's basically what's being retrieved, how is it being summarized, or is it being used raw, how is it being done for training data, for example. And then we have how big our small the model is, so basically quantizing it. So basically what we the main focus was to minimize cost, both computation and basically size of the model. And then we also need to make it as better as we could. So those are the four basically things that we chose, and we made those for automatic. So now if we can maybe, yeah, so the main contributions are, six phase autonomous pipeline. So of course we also need to then evaluate how good it is. So a six-phase autonomous pipeline. So we have dynamic context engineering. So that's basically depending on the query, the context, you can engineering what you need to feed the model. Um, Supervised fine tuning to improve the model's accuracy, basically in terms of its internal knowledge, and then quantizing it, so making it as small as possible, and then evaluations. Um, so yeah.
Yeah. So I think I want to add one thing before you move into sort of like explaining all of these tools and the pipelines that they have. But I want to explain something, that why is auto or self-evolving very important, right? Because essentially the idea is that if we can get the structure right, right, which is in at least in our way, we would say enterprise specific in terms of what the structure is. When we say structure, we mean how should it self evolve, right? Where is it getting its data? how is it how is it sort of like cleaning that data? How is it training itself? How is it defining its policies? That's what we call structure. But given that you have sorted the structure out, the thing that helps a lot afterwards is that machines obviously can iterate much faster than us giving that input and us being involved in that process, right? So we can actually have these iterations done over and over again in matter of like days to sort of like improve the performance. That's number one. Number two, we feel that since our focus is primarily what happens within an enterprise, within a domain, right? So in that scenario, context is ever evolving, right? I think there is an understanding that needs to be, or context that needs to be placed in, that enterprises are not like a machine, right? They're often thought of as a machine, but they operate more like an organism, right? it's reacting to its external environments, right? So there's always that back and forth. It's reacting to what's happening outside, and then that is changing the context of the context around the enterprise, and then everything has to evolve based on that, right? So henceforth, a system that is really and truly autonomous with a lot of sort of like tools that it has at its behest to choose which direction it wants to go into, I feel like gives a very important uh, or a powerful sort of like application to everybody in the enterprise, because you can rely on a system to evolve and doesn't need to be like a human involvement, right? So I think one thing that I always believe is that, and by the way, this is something that you and I discussed when we met the first time, where I think I said to you, I don't really want the models to be very intelligent, right? As long as they can iterate as many times as possible, right? I don't. The thing is, you and I, when we sit down and when we want to identify who's smart and who's not smart, right? In those scenarios, we sort of like discuss when we have given an instruction or like we've said something. Uh, how little time does that human take to reply back an answer, right? And how quickly it was that person was able to understand what we just told them. With machines, why do we have those expectations, right? Why have them be zero shot when they're not operating on the same time zones as you and me, right? They can just iterate very very quickly, right? So instead of focusing or obsessing over like very intelligent models and very intelligent systems, as long as those model can iterate correctly, I can have any model, right? Or at least most small models, I can have them perform as well as a large model, right? It is the iteration that really matters, and not the intelligence of those model and having like these big models to summarize my emails, right? We don't need that, because I can have those iteration do the same thing as long as it is able to iterate properly. And I think the industry, by
Sorry,
the way.
on that point, yeah. So
Yeah.
computers weren't made to do tasks exactly as humans. They were made to do the
Yeah.
grunt work that they can iterate over thousands
Yeah.
or a
Yeah.
countless amount of times. And
Yeah.
specifically, I think this this basically zero shot inferences were never an intended consequence of these larger models. As the
Yeah.
models got bigger and
Mm.
bigger,
Yeah.
this was sort of like I wouldn't maybe call it a side effect, but it wasn't really intended. These
Yeah.
basically inherent qualities that come
Mm.
out, which
Mm.
they weren't expecting to. And now
Yeah.
it's sort of become the norm. You need to have those huge models, and you need to have those
Yeah.
zero shot capabilities, which
Yeah.
wasn't really, yeah, to your point, wasn't really why computers were
Mm.
created. Yeah.
Yeah, no, I agree.
Sorry.
I agree. I think, I mean, essentially, the way we look at machines is like, they're all computers and all models from me are calculators, right? Essentially. And it's just to overthink them or to think them of like, by the way, I think on like a pure philosophy terms, I think there is a confusion that we have, which I think my very strong belief is that there is consciousness and there is computation, and those two things are very different from each other, right? And I feel like we were trying to achieve a degree of consciousness through sort of like a hardware, and a hardware with a software that essentially operates like a computer, like computation. It does
Yeah.
computation, and we somehow think that there is going to be like a degree of consciousness. And I think that idea is very dangerous, because also right now, I don't know if you're following, I don't know if you can add that as part of the video, but have you seen how even like Nvidia and Palantir and all of these large companies are sort of like turning on frontier labs, and they're like, yeah, we should use open source smaller models, because everybody wants their data to be protected, and these models are too large to do this, because we forget that what exactly were we trying to do in 24-25. In 24-25,
Yeah.
we were trying to build AGI. That's what it was, right? We were trying because we thought that once we have AGI, it will solve all the remaining problem, including the cost of running the AGI, right? Because you achieved singularity. And I feel like that's where it sort of like went off the rails, because once we realized that we're not achieving AGI with more computation, with more sort of like data, now we're stuck with these models that everybody sort of like is kind of like, putting down our throats that, this is what we need to use, and like Mythos can break this and Fable needs to sort of like, who needs those models, right? We don't need those models. So I think
I mean,
that's
and
the,
also I think these main ideas, one single entity or a single larger
yeah,
intelligence solving
yeah, a
everything, mostly
monolith.
comes from Hollywood.
Yeah,
It was never
yeah,
meant to be. Yeah,
yeah.
it was
Yeah,
never
I
meant to
think
be.
this, yeah. So the whole idea of like, super intelligence being a monolith, I feel like that's where things went off the rails, right? It's just like, it's I think no human is super intelligent, right? But us as a civilization is what makes us super intelligent, right? So why do we assume that digital systems are going to be different, right? Why shouldn't super intelligence look like swarm of smaller models, bunch of AI agents all working together in sort of like an architecture or infrastructure, which produces the end result of super intelligence, right? Which sort of like takes things forward. And I think
By the
that's
way, this is
something.
what we were trying to. This is a
Yeah,
smaller version of a.
yeah.
Yeah.
Yeah, so I think it's self evolving. That's kind of like what the idea is, and that's kind of like the thesis of the company too, which is that can we build a self-evolving civilization of AI agents that are responding to the external environment and then improving or retraining themselves and adapting based on that, right? It's kind of like inspired by Darwinism, where you need to respond to the external environment, which will determine what you would look like and what you would do. And that's kind of like, this paper is sort of like one of the first things that we did. And as I suppose we proceed into the video series, as we have been enforced to do, I think we will talk more about like, where we are on that level right now. But I think let's just jump back on this. So if you want to explain the how the model actually, the pipeline actually works.
So basically, we needed a trigger firstly. So firstly, we have some data. So let's maybe I'll just separate inputs. So basically most of your inputs are documents, so you have some new knowledge that you need to have the model learn. Now since we were trying to decrease the amount of computation needed and the amount of resources, so I think firstly we identified if there even was a problem to solve. So firstly you
Yeah.
get some documents. And then you generate a golden set firstly. So basically you just generate an exam paper for the model to examine it and see how bad it's performing. Does it really need the stick or not? Does it really need any training, or is it just performing well? This certain threshold is set by the user. So if it's performing on a knowledge base about 70-80% or 90% or whatever the threshold is, we don't train on it basically. So we skip the fine tuning part. But then what we do is then we basically embed it, chunk it, and then we save it inside a vector database to basically use for RAG later on. If it's the other case, then we need a supervised fine tuning data set. So a document comes in, we then generate a question answer pair. We generate question answer pairs on them. So basically, we give it to sort of like distillation. I maybe it's exactly distillation. So basically, we give it to a slightly better model, and then we say generate question answer pairs for this document, which we then train on the smaller model that we're trying to do this for. So here we were using a zero point 0.5 billion, so a 500 million model. And then so basically it's then chunked and then saved into the vector. And then you do like a drift detection. If it's below the threshold, then you do a supervised fine tuning. So we also needed, in our earlier experiments, we were finding that fine tuning hyperparameters is also like a problem. So we said, why don't we do auto optimization on these as well? So we basically used Optuna. So it's stochastic simulations basically. So it does a certain amount of steps prior to doing the exact fine tuning, and it basically, given those smaller samples of training, it then tries to find a good solution to the hyperparameter grid basically. So it selects a nice value, which isn't guaranteed to be the best one, but it's quite nice.
Yeah.
And then we
And by
do.
the way, that's also kind of like the point, right? The point is that why should we determine what is the right sort of like approach? Let the model continuously use all of these tools, decide for itself at which given point what does it need to sort of like work on, right? So in simple terms, and I'll try to simplify these things, Amar, as we move forward. In simple terms, let's take an example. Let's say that the model has been given the objective that you have to ensure the highest accuracy and while minimizing the compute, right? But we have as our priority defined accuracy as one of the major objectives, right? But tomorrow we might decide that, you know what, we don't need a higher accuracy than this. Now you just go focus on now we just focus on sort of like, reducing the size, right? The compute,
Reduce.
we're running out of compute, so the model is now working towards compute, right? So the objectives that it has can sort of like vary based on the external context. Henceforth, it can't be a fixed sort of like it can't be sort of like a fixed what do you call it, can't be like a fixed pipeline, or like a, it
Fixed
can't be like
metric.
it can't be like a scalar value, right? It needs to
Yeah.
be dynamically sort of like improving, right? So essentially that's kind of like the idea here.
So yeah, so we train on the supervised. We train on the hyperparameters that we get from the auto-tune module, and then we do reinforcement learning. So we have options for GRPO and DPO, but currently we've tried GRPO with the GSM 8K dataset for mathematical reasoning on the model. So that's optional if someone wants to do that, but it's part of the pipeline. And then we have a benchmark suite, so that basically we have configurations on what you want to evaluate. So we have root scores and similar metrics that are used for LLM inference. And then we have LLM as a judge. So that is basically the golden set that we generated at the beginning of the pipeline to check, how much we've improved on it. Um, this also has basically visualization pipelines, and then observation pipelines on how the training is doing, and what the parameters currently are. Yeah. So basically, in the RAG pipeline, we evaluated the chunks based on how diverse they are. So basically, what we're trying to do is that, every model has a certain context limit, and what we're trying to do is get as much information inside that context. So the more diverse it is, the better, because you cover a lot of concepts. And then redundancy should be decreased, so we don't get redundant information. So basically, we improved using DC. We used ragged 10 as well. So DCE improved that about 13%. Redundancy was improved about 6%. Token efficiency, it's that, the amount of tokens utilized when generating answers. So that was improved by about
Yeah.
7.4%. And yeah, the recall was decreased, and then the chunks used was improved about 23%.
Yeah.
Um,
And by the way, I think it's
so
important to explain the
this
audience
is
also.
something that was.
Sorry, I was just saying that this is important for us to also explain the audience that the benefit of, token efficiency and recall coverage and diversity and even chunks used is just on cost and compute, right? You save a lot of money on cost and compute, especially if you have agentic systems where there is, you have to do a lot of retrievals at all times. This is what this helps with significantly in.
Yeah, yeah, no, definitely. So if you, so basically this pipeline dynamically improves the context. So when you get some chunks, you then rearrange them. You either re-rank them. You make some, you rule some of the chunks out because it has redundant information. So all of that is basically your token saved. So your token saved is
Yeah.
equal to your dollar saved on inference. So if you're not doing this, then basically you're consistently using context that you may not need, um, or sometimes you're using context that is clouding the model's inferences.
Yeah.
So yeah, so that's basically dynamic context engineering. And then yeah, so we if you go towards auto quantization, so that's
Yeah, I think
you have
this is
floating point
interesting.
16,
Yeah.
so that's 16 bits. Yeah. So there's no compression. So but basically, you have the perplexity that's 91%. That's 91, and then you decrease to 8 bits. So its size decreased less than half. So that's even lower than half, and so that's about 1.82 compression rate. And then the perplexity doesn't move too much. So right now we're only using perplexity, but also we plan on doing this, for a detailed evaluation for this as well. And then you have 4 bit,
And
and then
do you
the
want to also
complexity
explain?
increases a lot. So
Yeah, do you want? I was just saying, should we also explain what perplexity is? So perplexity, in simple terms, means how shocked was a model to see something, right? How much was its confidence in terms of what it was generating, right? So when you have lower perplexity, it shows that you are really confident in terms of what you are sort of like producing. So this is sort of like one of the major benchmarks that we have. Yeah. Sorry, continue.
yeah, so this is basically how well a model predicts a sample of text. So how
Yeah.
well was the prediction? Yeah. So then we also did a model evaluation on domain questions, and then we basically
Yeah.
have average scores on how well the models performed. So the base model had about 5, and then just with the fine tuning we have about 6 average score, and then with combined with supervised fine tuning and RAG we have about 7 average score. So win rate is increased about 51% from the base model. The questions one is about 72 out of 141, while you can see the base was only about 22. So we get about 26% improvement overall with supervised fine tuning. With just inference or with just fine tuning without RAG, we get about 20%. So basically we improved a lot using these techniques. So this is
Yeah.
basically proof that we get
Mm.
improved
And across the board, it was
accuracies.
able to.
And then
Yeah.
yeah.
Yeah, no, makes sense.
So basically, this is
So,
just like a point 0.5. What I think what needs to be highlighted is that, just this is just a point 0.5 billion model. It's just 500 million, in
Yeah.
comparison, if you just go to uh, GPT-4o, for comparison, is 200 billion. So that's an insanely small
Yeah.
model. And this is basically proof that just
Yeah.
by fine tuning some engineering around the context and giving it in the perfect, not even a perfect, just a normal, a better way. You can save costs, you can bring improvements inside the model. And this is just, this is continuous
Yeah.
evolution as well, so this can be iterated over and over.
Yeah. So just to, I suppose, conclude on this, I think the idea that we've had around auto evolving has been that you need to sort of like have a system architecture infrastructure where it already knows what the objectives are. It has access to all of the tools to rewrite itself to match the situation that it is in, right? Essentially, and we started off with four of the most popular machine learning techniques, right? Fine tuning, reinforcement learning, quantization, context enrichment, and we automated all of them, right? And just to see how the system works, right? And the system performed as we were hoping it would, which is that it was able to achieve the same objectives that we gave it, which is reduce your size as much as you can, do not compromise on the accuracy, and keep doing that until you have achieved this goal, right? And find us that equilibrium where you can achieve that and then go live, right? And it kept sort of like doing that. And then, for instance, in our current deployments, because this is the paper was written some time back, but in our current deployments, this is something that has been sort of like going on, right? It's sort of like with the new data, it keeps on improving itself, keeps on achieving new and new objectives. So this is sort of like the earlier, I would say, the first emergence of, I would say, uh, value of open-endedness, right? This shows where we could go potentially from here as we add more and more tool for its performance. So I hope this was educational for the audience and also for our team. Um, I hope we are able to explain to the general audience that what our thesis is, and I think how the industry is moving more towards what some of us were saying for some time, and I would say academia was saying this for some time, right? They were not taken seriously for the last 12 and 24 months, I would say. But academia is now having their time in the limelight because they were right. The approach that we were all taking, I think, makes a lot more sense than just focusing on compute and data. And we think that systems will outweigh pre-training, right? Just a better system, better pipelines will eventually outweigh uh, just pre-training and the strategies that we have been following so far. So thank you so much. And next time, I think we will be the next paper, Amar. Which one do we want? Do we want to do separation of intelligence or do we want to do muscle memory?
I think, yeah, maybe we'll see.
Yeah.
But yeah,
which which
both
one
are quite
churns
exciting
yeah, which one churns us better
targets.
results for us to see. And so I think whichever shows us better results will bring that to you guys. Okay, guys, thank you so much. Until next time.
Yeah. Thank you so much, guys. Thank you.